Well, our first speaker today is Yue Cao. Yue completed his BS in EE and Math in 2011 at the University of Tennessee, Knoxville. He completed his master's in electrical engineering in 2013 here at UIUC. He's now a PhD candidate working under Professor Krein, and his interests include power electronics, motor drives, energy efficient buildings, and energy storage. It looks like we're going to hear about two of those today. He has interned with Oak Ridge National Lab, Flanders Electric in Indiana, and most recently at Halliburton last summer. Past projects include multi-level converter interfaces with solar panels, battery electric vehicles, and drives for mobile refrigeration applications. UA also served as a PESPAL's chapter president and also as the Pecky University Relations Chair. So
yeah, used to.
Thank you, UA.
Okay, thanks for coming. Hopefully this is an interesting topic. So this is something new, in my opinion, in the recent years, and I hope this is a first cut of my research. A lot of work to be done, but it's important to introduce you about this topic and what is the application and things like that. So let's get started. So background. We're all sitting in this so-called net zero energy ECE building, although it's not net zero yet because the solar panels are not on there yet, but there will be. So why do I care about the energy, the building energy? Because 40% of annual US energy is consumed in residential and commercial buildings. This is significant. And to those of you not sure about what is net zero energy, it means the total amount of energy used by the building on an annual basis is roughly equal to the amount of renewable energy created on site. Okay, and when we talk about energy efficient building, we usually think about solar panels and the grid. But my next question is, what happens between the solar panels and the grid? Okay, so we all use this energy. They come in the source of lighting, computers, appliances, and most importantly, the air condition, heating, ventilation system. So the trend now is everything going smart, right? Smart grid stuff and smart appliance stuff. But from the energy conservation view, thermal energy is the final form. All the energy that you are not used becomes thermal energy eventually. So our building is actually a big thermal energy storage. I think this diagram validates this. Well, this pointer is not. So it's pretty straightforward, right? So I want to talk a little bit more about the building thermal storage. Building thermal storage, in my definition, is a thermal inertia as an electrical swing bus, allowing temperature control for short time periods, while roof solar panels cannot provide constant power. Okay, this is important to know. It's a thermal inertia. It's a electric swing bus. What does this mean? Is we do not need the building to draw power from the grid during short periods if the thermal energy in the building can balance what is lost from the solar panels. So what is the benefit? Such inertia helps alleviate the need for fast varying controlled grid side resources, which are inherently expensive. And we only need the grid power when extended shading occurs. So is this something like a low pass filter problem? I'll leave that open-ended. I'll talk about that a little later. So my next question is, how does power electronics play a role here? First off, we have to acknowledge power electronics energy conversion technology among different units. The solar panels has to go to the converters, and And power grid also needs to do AC/DC rectifier and go through the AC motor drive and power the HVAC system. So that's one aspect. Also, if we use power electronics a little smarter, we can control energy flow based on weather pattern, building temperature, grid availability, user demand. And I mentioned the low-pass filter thing. And once we identify that interest region, we can feedback that to the converter controller to control the energy flow. So this is why power electronics plays a role here. So exactly what happens to the solar energy? We want to use real data to talk, not just some random guess. So in the past, Professor Pilawa and his student Rod have done significant work collecting solar data on the roof of the Everett. And we have two solar panels. One is their BP panel. One is connected to the Keithley meter. This one is a 100 Hertz full sweep, which means it collects open circuit voltage, short circuit current, and maximum power point, and also temperature. And another solar panel connects to the Agilent. That's for 5 kilohertz short circuit current data. So what do these data look like? For example, on November, I forgot to mention, it's an 18-month worth of data, and each day is more than 4 gigabytes. So thanks to the technology today, we have enough storage to do this. Total is about 2 terabytes. So for example, one day, this is a very good day, very clear day without clouds. The maximum power follows this ideal curve, and this is open circuit voltage. But on this day, it's a pretty bad day. See the lots of shading and things occurs, and the maximum power is pretty bad. And if we zoom here, we have very detailed data regarding this. So next question is, what do we do with this data? As I mentioned before, we want to regard this as a low-pass filter problem. So our goal is to find the interest bandwidth. So how to do that? Our intuition is do Fourier transform, right? So we can do a FFT here. And also, if it's a low-pass filter, we can think about some sort of low-pass filter. I'm using a third-order Butterworth filter. And in analog, it's actually LCL filter, which is commonly used for the grid-connected power electronics. So, what is the challenge here to do with this data? Number one is the weather pattern is very different each day, and we want more the data and analyze over a longer period. But we have a data storage problem. Also, the computer processing ability is very limited. So I'm trying to do as many days as I can, but so far I have 3D analysis that I can show you. So for example, the first one is, this picture is a 3-day short circuit current. Each day is for 16 hours from 4 a.m. to 8 p.m. So 3 different days. They are quite different in terms of pattern. And we do a normalized power FFT analysis here. And look at this Fourier spectrum, frequency spectrum. So notice the unit is millihertz. So under 1 millihertz, we see significant magnitude. And to give a better idea, 1 millihertz is roughly about 15 minutes. So what does this tell me? This tells me under 1 millihertz, it's too much to be filtered, right? So it's probably not a good idea to use just the thermal energy to balance the solar energy. It's probably something we have to deal with the grid. Anyways, I'll talk about that a little later. So if I apply a low-pass filter, for example, on the last day on there, this is a 1-minute filter, this is a 5-minute filter, and 10 minutes and 30 minutes. So looks like, yeah, this one is much filtered out. And here is, what is this? Yeah, the normalized short circuit current under different filter region, 0.1 second, 1 second, 10 seconds, and 1 minute. Notice a lot of energy is already lost if under 1 minute. And I have even more, like 5 minutes, 10 minutes, 15 minutes, and 30 minutes. So what does this low-pass effect essentially do here to us? Number one, it provides appropriate update rates for MPPT power converters. It tells like how fast my MPPT can update in order to collect the amount of data we need. And eventually they regulate the power sent to the AC motor drive. So we need to find a region of interest for thermal storage regulation. But how much energy is sacrificed, as I mentioned before? For example, 1 second, this is the difference between original data and the filter data. So if I only apply 1 second cutoff filter, not the whole lot is sacrificed, the energy is lost. But if I have a 5-minute cutoff filter, a lot of energy is lost here. Yes. Yeah.
So you're talking about a filter.
Mm-hmm.
So are you applying a filter that folks to just manipulate the data, or are you using the filter to model some thermal migration property?
Use filter to filter the solar energy, the fast varying energy,
So you're
and
actually filter on your circuit.
filter on the. I don't know how to answer that. Would you repeat your question again?
Well, I'm trying to understand.
Yeah.
If you're trying to use the filter for some energy purpose,
Mm-hmm.
or if we're just using a filter for some signal processing.
Oh, for signal processing purpose, I think.
And so you're trying to arrive at a model one. In other words, you're trying to eliminate frequencies that are important.
Yes. Try to find the interested bandwidth to update my MPPT power converter.
And so way back when, you showed the frequency spectrum, and the bulk of the energy is in the very left side.
Mm-hmm.
And so doesn't that tell you the answer, that that's where you chop everything else out?
Yes, that sort of tells me. But number one, that's only for 3-day data. We want to see if that's true also for a year long of data. Number two, what is a good cutoff? We're not sure yet. So we are looking forward to more work regarding how much energy is lost in terms of percentage, and pick a good cutoff. Yeah, that's what we are headed to. Yeah.
Let me comment a little bit. I mean, I don't want to jump in too much, but the question here is, you know, you look at the data and you say, well, I can cut this off and it doesn't look interesting after this. That's very qualitative. How much am I sacrificing? How many watt hours over a year? And then I can decide later, you know, is it significant or not? I mean, 1 part in 1,000 depends on how much it costs me to get it, et cetera, et cetera. So until you go through the details of trying to quantify it, you know, it's real easy to put those qualitative, yeah, I can chop the filter off here, but that's been the problem in this field for a long time. Everybody has their conventional wisdom about what's in the data. Not too many people are looking at the numbers. So we're trying to really quantify this. I think that's critical.
Yeah. Yes, and I want to continue on that. I actually have a preliminary energy sacrifice data in terms of percentage, but I found an error in my code, so I won't present it today. But we're getting there. It's something like this. So when there are more filter cutoff, you will see more energy sacrifice. So where are we? Yeah, and there's also question for this. There is a point we have to draw power from the grid. What should be that point? So that's sort of related to this question. And there's a lot of open-ended questions here. I just my first cut of my research. So some preliminary findings here. 1 to 15-minute bandwidth is ideal for thermal storage regulation based on what we have seen. About 15 minutes to be regulated by the grid as usual. And under 1 minute bandwidth, it's sort of insignificant for regulation. So the benefit here is eliminating the need for fast varying grid power, which means less cost. I want to also have these two open discussions here. Are we really saving energy? And number two, who is most benefited from this research? Is it the utility or the people sitting in this room? Or who pays the bill? I think it's the utility. Yeah, we don't know. Well, let's see. These are open-ended questions. Future work. A lot of future work to be done, I can imagine. This is a new topic. One is to build a thermal energy modeling. I'm taking that course right now and see how it responds to the solar energy supply. And also we want to do MPPT implementation with this low-pass filtered energy feedback. Eventually we want to do some of the drive work and see how that respond to the filtered data. And the one thing, once we get in the hardware implementation stage, one thing is interesting to see is how this effect on human bodies under temperature and noise changes. Like, how much energy can the building thermal storage give, right, without affecting our comfort very much. Also, the noise changes. If we constantly change the fan speed, how do we know, is it noisy or is it annoying? These are open-ended also. And even a little further down the road, maybe do some Monte Carlo prediction and do some predictability stuff, which Professor Alejandro Garcia may be interested. Acknowledgement, Simi and Professor Cry, my advisor, Professor Pilawa and his student, and my undergrad assistant, he also helped me some data analysis. So that's it. Right.
Are you proposing putting a low-pass filter on the solar panel with generating power? So for example, if you do nothing, no cloud, it's generating a lot of power.
Right.
The cloud will be valley, and you're trying to smooth that out.
Okay. So what eventually I think I want to do is under certain temperature pattern, we have different MPPT update rates. And given that update rates, we update the MPPT and supply the building energy. For example, it's a cloudy day, okay, and how to say, it's a cloudy day, and I noticed that, so I only update 10 minutes at a time of my MPPT, and whatever is lost is regulated by the thermal storage. Is that kind of clear?
particular source of that. Solar energy. So do you fall back to, what I'm getting at is, because the high frequency oscillation,
Mm-hmm.
even if I don't control it, I will still default to the low energy form of the source. I'm missing the whole concept.
Okay.
You want me to comment?
Yeah, could you comment?
Well, let me take an obvious thing from this data. Okay, I could take my power converter and I could close its loop at 5 kilohertz. I could update it that rate. I could track this data. Okay, and I can worry about stability and whether that really will work, and data rates and samplers and all the other stuff. Right? I can do what's very traditional right now and simply take my power converter and basically every second I make a decision to put a new set point into my maximum power track. And then I leave it that way for 1 second. Well, the power is jumping all around, okay? Until we have this data, until we have it all sorted out, I have no idea how much I'm giving up by doing that. So I can't talk to the person who says, well, a 1 second update is perfectly fine, versus the person who says, well, you got to have a 5 kilohertz update. And there's no information for either one of those. So if it turns out I only need to update the power converters every 10 minutes, okay, then the way that one would control it versus the dynamics on the grid as opposed to the dynamics on the solar presumably are fundamentally different. Right? If I need to update my solar at 1 kilohertz rate, then it's basically the fastest thing in the system. If it's 10-minute rate, then it's the slowest thing in the system. But even so, right, it's still going to be noisy because the solar panels are going to do whatever they do. So the question is here is what's the energy difference? In effect, do I care from an energy perspective? Ultimately, then we have to figure out, do we care from a dynamic perspective, right? Balancing instantaneous energy for the power grid. Slightly different question, but trying to put those two together with this data.
You had a previous slide.
Okay. Which one?
What do you mean by thermal storage regulation? What is your storage mechanism? Storage meter?
It's the total internal energy of the building. Think of it as like a capacitor. It's 1/2 CV square. But it's
The thermal inertia you're talking about is
like he's asking what is this thermal storage, right? Yeah, it is temperature. It's
I mean, I understand the building materials, those block walls out there, they store energy of the sun. So they absorb it during the day and they radiate it at night.
well, it's also what's containing here. Like you and me emit energy to the air, and the air itself has internal energy.
Okay, so I think about the thermal cycles on a hot summer day.
Mm-hmm.
It's very hot during the day.
Right.
Your air conditioning is running like mad.
Right.
But I don't see that you're storing energy for later use unless you're just talking about the effort you put into the building and you're counting that as.
No, suppose there's a cloud coming here. I can temporarily shut down or slow down my HVAC and just to increase the building the air temperature a little bit without causing the discomfort.
So you're trying to find out what thermal time constants are.
Yeah, that's in the area. Yeah.
And you're trying to identify, is it a 1 minute, is it a 10 hour?
Correct. Yes. Yeah, that's all open to this. Yeah. Yeah.
Okay, so you're trying to use the building as a flat bus, effectively.
Yeah, swing bus. Yeah.
Would it be interesting to look at some of the data ComEd has, like in the Chicago area, where they actually have a program where they can control residential AC to regulate those? Like, is this a similar concept? Because they actually have a program where they'll install something that can control your AC compressor.
Mm-hmm.
And so that they can shape, loads and that type of thing. So it's a similar concept to what we're talking about here, except you're not only considering peak load, you're considering solar generation as well.
Correct, correct. And yeah, that one is more on the usage and stuff, right? But this one is what we can get from the solar energy.
But we'd be shaving our building usage to complement the solar energy.
Yeah, they work together. Yeah.
I just wondered if there might be some correlation.
Okay.
Let me comment along the same lines.
Okay.
All the other programs that I've seen, maybe I'm wrong, are strictly on-off kinds of things. Your comment says, okay, I want to move your peak elsewhere, so I turn your stuff off for a while. That's not what we're talking about here. I can update the speed command to the fans for this room. I can update them 100 times a second. Okay, so I can move the power all over the place. As long as I keep the average the same, the temperature in the room won't change. So there's a bandwidth there over which you and I won't notice it. But I can manipulate the power, modulate it a lot. Maybe fast enough, maybe enough to track what's going on with the cloud cover and so forth, without you ever noticing. Now, I'm not going to do it with the lights, that'll drive you nuts. Right? We know that. I mean, I could do this, I could modulate the lights very rapidly, and we'd all notice it. But, you know, nobody's tried it with a fan. And there's actually a fair amount you can do with that. And that's a totally different, if you will, a bandwidth, different band selection than what ComEd is able to do. You know, ComEd can't do that fast enough to track cloud cover going by or flocks of birds flying over the building or anything. But I think maybe we can. We'll have to see.
Is part of the investigation just to determine kind of what the benefit would be, whether it's, you know, 10%?
That's the first thing is what's the benefit, right? How much energy we're talking about. The second thing, of course, is what do I need to do to present something very predictable back to the grid, which is what we've talked about as a group here on and off all semester, right? How do I make the whole load much more predictable? But then the third thing is, can I make this more and more even dynamically self-contained?
Okay. Thank you. All right. It's pretty new thing, and I understand there are a lot of confusion. Me too, actually. Try to understand as much as I can. So hope next year I'll give you another update. All right. Okay.
Well, our second speaker is Ben Macy. Ben received his bachelor's in electrical engineering from Valparaiso University in Indiana in 2013. He is currently working on his master's degree at UIUC under Professor Robert Palawa. Ben is interested in power electronic converters for electric vehicles and renewable energy applications. So look forward to hearing about Ben's switch-capacitor work.
We're good. All right. Thank you, everyone, for coming. We're going to talk to you about the work I've been doing over the last year, which is a 1.2 megahertz, 25 to 100 volt resonant Dickson switch-capacitor converter using GaN transistors. So I'll give you a brief outline. First, I'll talk a little bit about the motivation of this project. I'll talk a little bit about switch-capacitor converters and hard charging. I'll go over resonant circuits, talk about the Dickson topology that I'm using, and split phase control. We'll go over some simulation and hardware results, and then I'll end with some future work. So the motivation. So switch-capacitor converters, one advantage is that they can achieve higher step-up ratios with good efficiency still. So one application might be you have a lithium-ion battery stack, maybe for an electric car or something. So what you have to do is you have to put a bunch of these batteries in series. We know that when you have components in series, they have to share the same current. So maybe you want to have less in series and have some power electronics interface in order to better optimize the energy uses of each battery. So here's a picture of like the Tesla battery. So this is one way that you could do it. The output voltage is obviously going to be the battery voltage times the number of batteries in series times the conversion ratio of the converter. So why are we using switched capacitor converters to do this? For a lot of applications, like electric vehicles, the size and weight of your components is very important. So here's a graph that shows the energy density of components, inductors, and capacitors. As you can see, the inductors are in the left on the blue, and the capacitors are on the right. And this is a log graph, so the capacitors end up beating out the inductors by a factor of 100 to 1,000x. So if you can use capacitors as your primary energy storage mechanism in your power converters, you can highly increase the energy density, which means you can make the converter much, much smaller. So what exactly is a switched capacitor converter? If you've taken 464, you'll recognize the top converter as a boost converter. And the way that it works is that you modulate the duty ratio of the converter, and then that determines the output voltage. There's a lot of advantages and disadvantages. Some advantages are that this is widely used. There's a lot of integrated solutions to help implement these circuits. Voltage regulation is really easy because you just change the duty ratio. Some disadvantages, though, is that the switches have to be rated for the full output voltage, which is high voltage stretch, which means you can't switch as quickly as if they were rated for lower voltages. And the inductor is often large in these sorts of circuits, and it's often also lossy, which is obviously a disadvantage if you're trying to make a small converter. So what's a switched capacitor converter? The bottom diagram illustrates a simple example of a 1 to 2 step-up switched capacitor converter. So you can see during phase 1, you're charging this flying capacitor to the input voltage, and then during phase 2, you're charging the output capacitor to 2 times the input voltage. So you're essentially just using a switch network in capacitors in order to create a set output voltage. Some advantage of this converter is that it has lower device stresses. So all of these switches are rated for the input voltage instead of the devices being rated for the output voltage. The capacitors have higher energy density, which I talked about a little bit in the previous slide. Some disadvantages, though, is that this has a larger number of components. So here you have 4 switches instead of 2, which is going to be a disadvantage in a lot of applications. And these also have fixed conversion ratios. So with the magnetics-based controller, you can just change the duty ratio in order to change the output voltage, which helps with regulation. For this implementation with switched capacitor converters, changing the duty ratio isn't really going to change the output voltage in the ideal sense, because the output voltage is just going to be twice the input voltage. So I'll talk a little bit more about some other disadvantages of switched capacitor converters and what we're doing to mitigate those. The first is hard charging. If you're charging a capacitor with a voltage device, which is a capacitor or a voltage source, the instantaneous voltage difference is going to be across the parasitic resistance in that network. So here, this is a simulation where we're just closing this switch. The initial voltage across the capacitor is 0 volts. So the entire voltage difference is across this parasitic resistance. So it results in a large current spike, which is very lossy and which is very undesirable. So you can see that it's a large current spike, and then it's an exponential decay, which we learn in basic circuits. So having this characteristic, it's very troublesome for switched capacitor converters because we have this inherent trade-off where the energy in a capacitor is a half CV squared. So the amount of energy stored is very high, but it's proportional to the voltage squared. But the energy loss in a switched capacitor charging like this is a half C delta V squared. So if we allow the voltage of the capacitor to ripple a lot, then we're utilizing the energy storage capabilities of the capacitor. However, we are losing a lot of energy when we're doing that transfer. So this is kind of an inherent disadvantage when just charging capacitors like this. However, there is a solution to this problem. There's a few solutions that have been explored in literature. One is using a current device in series with the voltage branch. So here we add this inductor, and it ends up that we can make the inductor, if we choose the size and the frequency of the converter, then we can make the circuit resonate. So here we can see by adding this inductor, what we do is we have this sinusoidal current response. So we eliminate the current transient that we were talking about before, and that helps reduce. And also an advantage of this is that it also helps reduce some of the switching losses, because one component of switching losses is the voltage over a capacitor and the current through a capacitor as you're turning the capacitor on and off. But as you can see here, if we choose the times where we turn the switch on and off very well, then we're going to have zero current through the switch at that instance. So we're not going to have those losses. So there's obviously, like, that's a basic switch capacitor converter. There's a lot of different topologies. The one that we're using here at Illinois the most is called the Dickson topology. And we're using this for a few reasons. One of the primary reasons is that we can introduce resonance with only one inductor. So we can have an inductor here at the low voltage side of the converter, and then we can achieve resonance in the converter through that inductor. Another advantage of this is that we can explore different control techniques for switch capacitor converters. So traditionally, you just have two phases where you're switching one phase to the next phase. And I'll talk a little bit more about that later and why that's important. So let's go over some basic converter characteristics of a Dickson converter. And this is a 1-to-4 Dickson converter. So you can see there's two phases, or in a lot of cases, you'll have two phases to the converter. You can do some basic analysis to find out the voltage of the capacitors and the voltage of the switches by looking at some steady state analysis. So you can see here that VC1 is 1 times Vn in steady state, assuming that you're operating this correctly. And then here you can see VC2 is Vn plus VC1, which is again Vn, so it's 2 times Vn, and then similarly VC3 is 3 times Vn, and the output voltage is 4 times Vn. For this particular topology, all the switches are rated for the input voltage, except for 2 of the switches, switches 6 and 7, which are rated for twice the input voltage. So again, comparing that to a magnetic space converter, all of the switches are going to be rated for the output voltage. However, if you look closely, you might see that there's still an issue with this particular topology, because we have C1, C2, and C3 making a KVL loop. So they're all voltage devices in this loop. So like I explained earlier, when you have that, you're going to have the voltage difference is going to be across the parasitic resistances in that network, which is undesirable. And again, in the second phase, we have this happening again. So we expect that we might see some current transients in these two paths for this converter. So we can simulate the converter and see exactly what it's doing. So as we expect, we are seeing a sinusoidal current at the inductor of the converter. However, because of those KVL loops with all the capacitors in series, we're still having these voltage transients because the voltages at the terminals of a switch when it's turned on aren't equal. So we have these large negative voltages, and then we're doing our resonant response here, as you can see. However, there is a control algorithm that we developed here in order to mitigate this. So instead of just switching from these two phases here, what we can do is we can implement subphases where we are allowing the voltages in the KVL loop to equalize before we change to the next phase. So for example, in phase 2B here, this point here, the voltage is rising because current is flowing this way into the capacitors. And then when the voltage across the switch here is 0, then we can close that switch and we can connect this other branch to the first capacitor. So by doing that, we're going to eliminate the current transient because the voltages in the KVL loop are equal at that point. And we can do a similar thing in these phases here. So what exactly happens in simulation when we do this? When we delay, what we do is we end up delaying the turn on of one switch. It's a switch that's in the KVL loop when we're implementing the control. So you can see here that this is the control signals for switches 1, 3, and 7, and then there's a delayed signals for switch 5. So you can imagine this switch is on, and this switch is on, and this switch is on. So you can see that C2 and C3 are being charged while we're waiting to turn switch 5 on. And you can kind of see the delay here in the picture. So by waiting, you can see that we're eliminating the current transient that we're seeing there. And here's another plot that might help you understand why that happens. So this is the delayed signal, and then this is the voltage across switch 5. So when we're changing to turn these top control, when we're controlling these top switches and turning these switches on, this is the voltage across switch 5. So the blue is the voltage at the drain, and then the red is going to be the voltage at the source. So we're waiting to turn switch 5 on until these voltages equalize, and then we turn the switch on and it behaves correctly. So you can see that the current transient is indeed eliminated. So this works well in simulation, but we obviously wanted to go ahead and build this and test it out and see how it worked. So you can see the size of the converter here compared to a US quarter. And this is a fairly small converter. And it was designed to be 100 to 400 volts, and it was going to operate in resonance. And then we wanted to push 1.25 amps at the output and switch this thing at greater than a megahertz in order to minimize the component sizes. So here's a little bit more explanation about the different components. So you can see that the inductor is relatively small compared to these capacitors. So this is indeed like the capacitance dominates the size of the converter. However, it's also worth noting that these capacitors are all metal film capacitors, which have lower energy densities than just ceramic capacitors. So I've also recently done more work with ceramic capacitors, which are much, much smaller, maybe the size of one of these pads here instead of 2, and then maybe one of these pads instead of the 5. So that gives further room to increase the energy density by reducing the size of the overall converter. In order to get a good metric for how power dense this converter is, we measure the size of the power stage. So this includes all the capacitors and the inductor and the gate drivers and the switches. So it ends up being 0.26 inches cubed. It's worth noting that this doesn't include some circuitry. It doesn't include the level shifting circuitry that we're using and the microcontroller. And we don't do this because we think if this was going to be commercially available and commercially used, that a lot of the control circuitry might be integrated into a smaller package. So for example, a lot of magnetic space converters have a single package where it might be a controller and a driver and a switch all integrated into one package. However, since this is an area of research, those things just don't exist yet for these sorts of converters. What happens when we test it? We can indeed tune the frequency in order to see this resonant current effect that we expect, which is good. That means that we're achieving our zero current switching, which is going to reduce switching losses, and it's going to help us out by reducing hard charging. And then, so what parameters are we able to achieve? I was able to get this thing going from 33 volts to 117 volts. If you do some quick math, you realize that isn't 33 times 4 isn't 117. The reason is because switch capacitors, the model is having an ideal transformer and then an output resistance. So you're never going to achieve the full conversion ratio with your capacitor if you have a lot of current flowing through it because there's going to be a voltage drop across that resistance. And that's an area of future work where we're working on doing some output voltage regulation. And I was able to do 264 watts through the converter at a frequency of 1.2 megahertz. So if you do the math, it's about 1,000 watts per inch cubed, which is a very high power density, especially in the research world. And you can see an efficiency plot here on the bottom too. The peak efficiency is about 92%. So back to the power density. This is a log-log plot of the research done here, which is the green circle, and then some other papers that have been published in their power density figures. So you can see here that we're up here at about 1,000. There's another really good paper from Virginia Tech here using some integrated inductor design on a PCB. But besides that, we're doing pretty well against a lot of the other research that's out there. Like I said, I'd go into some challenges in future work. I'm working on increasing the voltage and power through the converter. We're still seeing some undesirable behavior. There's some ringing that's happening in the converter due to some parasitic inductances, but we think that we can figure those out and help mitigate that. And that'll help us achieve the higher voltages that we want to get to. The level shifting, like I said, right now we're using kind of these big analog device chips. We don't really need all their capabilities. So we're working on doing something in discrete right now, and then hopefully maybe doing an integrated controller in the future. And working on doing something more interleaved to help reduce the output capacitance and get some more power through a converter like this. So thanks for coming, and I'll answer any questions that you may have this time. Yeah.
So 8% loss at this level is like 20 watts.
Yeah.
In a quarter of a cubic inch. You've got a lot of thermal stuff to handle. How is it distributed and how do you manage it?
Yeah, so exactly. That's really the limitation where we are right now is managing the thermal losses. So right now with the setup, I'm using a fan and to push this much power, I was using the great resource of another graduate student blowing the converter with some duster in order to reduce some of the thermal losses as well. But I mean, without that even, we're getting around 170 watts through it. And it's getting hot. I mean, it's getting to 100 C, but that's another advantage of using gallium nitride transistors is that they can operate at these higher temperatures. So yeah, that's definitely an area of future exploration where we're thinking about maybe doing some liquid cooling and some other ways to help keep this thing cooler and push more power through it.
Let me chip in. One of the key benefits of the switch capacitor converter, in addition to all the switches being rated for less than the output voltage, is now spread out. So, in the regular converter, you have one switch or two switches, and then you beat the crap out of those things, and they will get very hot, and that will be one hot point at advantage. Now, if you look at these things, so the shiny things are the gallium nitride switches, but each of them is dissipating some energy, but overall, you spread it out through a much larger volume. So that's a nice side effect that you don't normally consider, but when you're trying to push extreme power densities, it actually is a significant benefit of switch capacitor approach. You spread the heat generation around, makes it much easier to cool.
Any other questions? Okay, thanks again for coming. What?